Can you hear me?
Yes, I can hear you.
Okay, yeah. So we'll just wait for a few more minutes.
We can hear you, yes.
Okay, yeah. So we'll just wait for a few more minutes for people to join in. There's Sourav, who is another of the organizers. I think he was also in touch with you. Right there. And
hello.
Hello, Sourav.
Hello, hi.
okay, Sourav, so we'll wait for just one more minute because
yes, I think we should
logging in. Yeah.
Yes, I think we should wait for a few minutes and then start.
I had a technical problem for some reason. My laptop camera is not starting, so I have to log in from two places.
But this camera is better.
Okay. Yeah.
Makes you look more like a scientist. So it's nice.
Vladan, also this is live telecast on YouTube, and there are a lot of viewers there as well. So I'll send you the link after the talk.
Great, thank you.
Okay, Sourav, should I start?
Yeah, but yeah, okay, let's start maybe slowly.
Okay, so yeah, so I just had a small few notes because I had a few things to say. So it's a great pleasure to introduce Professor Vladan Vuletic, who is currently a Lester Wolf Professor of Physics at MIT. So Vladan was born and brought up in Serbia. I think at that time was Yugoslavia, and did his studies in Germany, eventually moving to US. In particular, he carries the legacy of two big schools with two big stalwarts, Professor Ted Hunch at the Max Planck Institute of Quantum Optics, where Vladan did his PhD, and then later he moved as a Leiden postdoctoral fellow at Stanford with Professor Steve Chu. So he started a faculty position and his laboratory there at Stanford, but soon shifted to MIT, where he has been working for almost 2 decades. And also he is currently the co-director of the Harvard MIT Center of Ultracold Atoms, or CUA in short. So Vladan in some ways has one of the widest range of interest and specialties in AMO physics. Like any of us would be elated to be specializing any one of these fields. Vladan freely moves between ion trapping, on-chip BECs, quantum metrology, spin squeezing, cavity QED, atoms in fibers, and also lately many body physics and strong interactions with Rydberg, strongly interacting photons with Rydberg atoms, which we'll be hearing today and in the next lecture tomorrow. So in each of these fields that Vladan touched, he made seminal contributions, starting from seeing very early signatures of Efimov states in cesium. It's reached Feshbach resonance, which eventually led to the cesium BEC, setting up the entire field of cavity cooling and mesoscopic cavity quantum electrodynamics with many atoms, seminal contributions, spin squeezing, atom-ion collisions, to even shedding light. This is one of his more recent and very fundamental work on understanding friction at a microscopic scale with atoms and ionic systems. In some ways, I was very lucky to be a postdoc with him. And when I was choosing, several people in the field said that Vladan is a poster boy of atomic physics. I didn't understand it till I actually saw him really working. And in many ways, in my little experience, he's the most complete physicist I have seen, because he's equally comfortable in debugging grounding issues in the lab with electronic circuits, and at the same time, making exactly solvable analytic problems. Like, I've seen people doing simulations simultaneously, but he's extremely, this is something I think maybe it's not very well known, but he is actually a very analytic, calculating physicist as well. So Vladan is also an outstanding teacher, and in his classes, I've seen few, he engages students with series of brain teasers that engage everyone, and before one knows, actually starts learning. So that's what we'll be listening. And today is the first lecture, and tomorrow the lecture, actually the second lecture, the follow-up and the last of this series will actually start at 8:30 instead of 8 Indian time. So with that, over to Vladan. It's a pleasure to have you here.
Thank you very much, Saikat, for this very kind introduction. It is great to see you again, and I certainly miss the times when we worked together on subjects in quantum optics. Today and tomorrow, I would like to tell you about one area of my interest, which is Rydberg mediated interactions. It's titled Atom by Atom and Photon by Photon, and this is really in two parts. Today, I would like to tell you how we can use Rydberg interactions in combination with the phenomenon of slow light and electromagnetically induced transparency to implement quantum nonlinear optics, and I will also define what that means. And then tomorrow we will focus on using the same Rydberg interactions to study many-body spin models, strong interacting many-body spin models with interacting individual trapped atoms interacting over distances that are optically resolvable using, again, Rydberg interactions. So it should show you kind of two sides of the same coin. Where we use atoms and light and the combination of those to either manipulate the light with the atoms or manipulate the atoms with the light. I invite you really please to ask me questions directly, either in the chat or even just unmute yourself and interrupt me. It will be much more fun for all of us if we can interact. And otherwise, I will also try to make some pauses. Okay, so the topic today is Rydberg interactions and quantum nonlinear optics. And so what is quantum nonlinear optics and how is it useful? So in general, you know that optical nonlinearities are very interesting and useful. You can, change the color of laser light. You can, take two photons and combine them into a single photon of a higher frequency. You can frequency double for various technical and other applications, etc. But even in the systems, even that we call highly nonlinear, some very nonlinear crystals require very large number of photons. These numbers are measured in the billions, many powers of. And so the question is, can we imagine having optical nonlinearities at the level of individual photons? Can we have a situation where two photons interact in some way so that the state of the two photons is distinctly different from the state of individual photons traveling through the medium? And if we can do that, it's not only valuable for fundamental understanding of quantum optics and in an extreme limit where the photons are no longer non-interacting particles, and it could be potentially useful for applications such as quantum networks, maybe small quantum information processors, etc. So, but it's primarily also, if you want, kind of an intellectual exercise. Is it possible at all to make systems that have these properties? So one way to think about quantum nonlinear optics is that if you plot along one axis the photon number, say increasing to the right, and then along another axis the interaction strength per photon, say in the up, then you can kind of identify four regions. Maybe the easiest region, the one that we are most used to, is kind of the number of where photon numbers are relatively small and the interaction strength per photon is very small. So we are here in the interacting in the linear optics regime where photons are simply non-interacting particles that where we just add the electric fields associated with them. And then if we increase the photon number and go to some nonlinear crystals, at some point, we reach this regime of classical nonlinear optics where you have effects like frequency conversion, frequency doubling, etc. And then, in the other hand, if you look at small photon numbers but somehow manage to increase the interaction strength of a photon, then we are here in this regime of quantum photon nonlinear optics, and this is mainly the regime where I will be talking about. So we will be talking about a few photons, but very strongly interacting. And then you can imagine a very interesting regime where both the photon number is large and the interaction strength per photon is large, and this would be a regime of where if you had a strong interacting quantum many-body system, typically you have strong dissipation and strong input-output coupling, and that's a very interesting area in itself for the future, I think. But today we will focus on these nonlinear optics at this few photon level. So, why is this so difficult? Why has it not been achieved? Maxwell's equations have been known for what, 200 years or something, or almost. So The problem is, of course, that the photons in free space just pass through one another. The interaction, the native interaction of photons in vacuum is extremely small. I mean, there is some interaction because you know that photons can create virtual, say, electron-positron pairs, and then the electron-positron pairs can interact. So there's a little bit of the polarization of the vacuum, but this interaction is extremely, extremely small, many, many orders of magnitude away from what we can observe. So in free space, they just pass through one another, and we just add up the fields of the photons. So it's clear that photon-photon interactions must be mediated by matter somehow if you want to make them strong. But at the same time, if you want to, keep the photon character of the field, a field that travels in a certain direction, etc., then the interaction has to be coherent. That means it has to be reversible. So somehow the photons need to be coupling to the matter in such a way that they can couple from photons to matter and back to photons in a well-defined and controlled way. Otherwise, it will just look like dissipation. So we need coherent interaction between photons and the matter. And also the other problem is that of nonlinearity, right? If you want to make a nonlinear system, then somehow there must be something that defines a quantum. And so in some sense, we need to involve in some way single atoms or single excitations at least to make nonlinearities, because if you have just many atoms that are interacting at the same time, then it will approximately look like a harmonic oscillator, and there will be nothing single atom or fermionic or nonlinear about it. So, but then, as I will show you in a moment, single atoms or single excitations interact only very weakly with single photons, fundamentally. And the reason for that is as follows. Well, an atom can be put into a laser beam or into a mode where the photon is traveling, and this atom has a certain cross-section sigma. And fortunately, this cross-section is large. So while the size of an atom is, of course, on the order of angstrom squared, the cross-section for an atom interacting resonantly with light is about 10 to the 8 times bigger, and it's on the order of the wavelength squared. So if you want strong interactions between photons and atoms, then you need somehow to arrange it so that the absorption probability, or the probability for the atom to interact with the photon in this mode, needs to be on the order of 1 or exceed 1 ideally. So the problem, of course, is that even though the atomic cross-section is large and it's on the order of lambda squared, it's a little bit less than lambda squared, the beam area, the area to which you can focus a beam, at least in free space, is limited by the diffraction limit, which is also on the order of bigger than lambda squared. And so that means that in free space, really, this ratio, the probability of an atom to absorb a photon, is at best in practice maybe 10%. 10% is about the maximum, the record that has been achieved in free space. So in free space, you have this problem that you can't focus down the beam any smaller than the atomic cross-section, because both are limited by lambda squared. And of course, one way out is cavity QED. You have heard presentations about that. I won't talk about it, but that's basically the idea that you place mirrors around the system, and then the photon can pass multiple times through the atoms. And if it has m passes through the system, m for the experts is given by the finesse of the cavity divided by pi. Then if you have m passes through the system, then you can have this absorption probability approach 1. So cavity QED is one way out of this dilemma of how to make strong photon-atom interaction. And it's possible to get to strong photon-atom and also photon-photon interaction in this way. The other way would be to say, well, instead of placing the mirrors around it, I could place n atoms into the laser beam. So instead of 1 atom, I have now the cross-section of n atoms. And now, of course, multiplying things by n, in principle, I can make the absorption probability for the photon to be 1. This product of the atomic cross-section sigma and n divided by area is what we call just the optical depth of the ensemble. So I can certainly put enough atoms in there so that the optical depth of the ensemble exceeds 1. But in general, when I put n atoms into the system, the nonlinearity is weak. And the reason why the nonlinearity is weak is simply because, I have now n atoms, and any of these atoms could have absorbed a photon. And so there's really nothing, if a second photon comes in, then that second photon is most likely to be absorbed by another atom, not by the first atom, and therefore these photons in general will not interact. So the basic idea of nonlinearities is, of course, that if you absorb one photon by an atom, then the atom is in the excited state. And now if a second photon comes in, then this excited state atom will not absorb the second photon. At best, it will, stimulated emission or something like that. So here, however, when we have n atoms, the nonlinearity is weak because different atoms can absorb 2 different photons. And this is where this idea of Rydberg atoms and Rydberg blockades comes in. So we'll be working in this regime, but somehow arrange it in such a way that in spite of having n atoms in the system, where n can be hundreds or thousands or 10,000s, we will still have strong nonlinearities. And I would like to show you how that works. So basically, I will be telling you about using electromagnetically induced transparency in combination with a Rydberg system or in a Rydberg ladder to make Rydberg mediated photon-photon interaction. I will be telling you about absorptive, nonlinear strongly nonlinear absorption, and also strongly nonlinear, or if you want, forces between photons. So just as a reminder, or maybe I hope you've seen it, if not, just very, very brief introduction what electromagnetically induced transparency is. So this is a nice review paper, but there are others. This is a widely studied field. So electromagnetically induced transparency takes a 3-level system with 2 stable ground states. And the most common is this so-called lambda system, although we will be working in this ladder system later, but most common is the lambda system, where the levels 1 and 3 are some atomic ground states, which are stable. Could be the hyperfine states, for instance, of an alkali atom. And then we have a strong absorption on one of the transitions. So you have to imagine that we place the atoms in the state 1, and then we have probe light coming in on a transition, on resonance with transition 1 to 2. And in general, these many atoms in the state 1 would absorb the probe light. And then by turning on a strong laser coupling the state 2, the so-called coupling laser, to another stable state 3, we can induce transparency in the system and create light with modified properties in the system. And this really goes back to pioneering fundamental work of Steve Harris from 1989. In some sense, it's a very interesting story. I mean, at this point, the Maxwell equations had been known for more than 100 years, and all this is just Maxwell equations. And yet nobody before Steve Harris realized the interesting physics that lies in this 3-level system, although the optical Bloch equation for the 3-level system were long known and anybody could have simulated it. And so what he realized in a slightly different context, he was looking for lasers without inversion, but this is the founding of EIT, of electromagnetically induced transparency. What he realized is that if on the horizontal line I have the tuning of the probe laser from resonance, and the dashed line represents the absorption of a 2-level system, like so, then the absorption is of course largest on the transition frequency. So this is plotting the imaginary part of the index of reflection, or the imaginary part of the susceptibility. So this is the absorption of the 2-level system. And similarly down here, the dashed line is the real part of the refractive index -1, or the real part of the susceptibility. So this is the phase shift that light experiences as traveling through the medium. Then for the 2-level system, we have this simple dashed line. But if you turn on now this coupling laser here, then what happens is that a transparency window opens up. In the ideal case, the absorption goes all the way to 0 on resonance in an otherwise opaque medium. So you have a transparency window here near 0 resonance frequency. And also the dispersion is now modified. Essentially, you can think of this as having now 2 resonances rather than 1. We have to dress the system. And so the dispersion that had 1 slope actually turns into an opposite slope of the index of refraction versus frequency. And also this window, I have drawn it here wide, can be in principle made very, very narrow, so that dn over d omega, the slope, is very, very steep. And what that means is that if you take this well-known formula for the group velocity in such a medium, then if the slope dn over d omega is very, very steep, if the index of refraction varies quickly with frequency, then you can have a situation, for instance, where the group velocity becomes very, very small, much, much smaller than the speed of light. And early work already established that people had made group velocities down to tens of meters per second or so, maybe 1 meter per second, so extremely low group velocities. So one simple way to think about this 3-level system is that what is really going on inside the medium is you no longer have the pure photon inside the medium, but you have what we have a quasi-particle, which is a coupled excitation of light and matter. We call it a slow light polariton. And it's really a quantum superposition between the situation where the photon travels in the medium. So you have a photon traveling at the speed of light c in vacuum. There are these atoms, these absorbing atoms. Here's the control field. And at the same time, what can happen is that the photon gets absorbed. And then there's a Raman transition where one of these atoms, as the photon is absorbed, is transferred by the control field down to this level. So now you have a collective excitation that we sometimes call a magnon. It's one of these atoms has absorbed the photon. However, what is special about this collective excitation is that you cannot know, even in principle, which atom has absorbed the photon, and therefore you have a coherent superposition of atom number 1 having absorbed the photon, atom number 2 absorbed the photon, etc. And what this allows you to do, and what this allows the photon to do, is it allows the photon to remember in which direction it is traveling. Basically, it's a phase coherent mixture of all these possible excitations that allows the photon to remember that it is traveling in the forward direction. If you had just one atom here, then basically after absorbing the photon, this atom would no longer know which direction to emit into. But in this system, we have this coherent coupling of light and matter where the photon remembers the mode it is traveling in. And so basically, if this magnon component is dominant, if there are many atoms, if the photon is much more likely to be found as stored as this collective excitation inside the medium. And this, of course, doesn't travel because the atoms are stationary. These are laser-cooled atoms. Then the slow light polariton velocity can be much, much smaller than the speed of light. So you can think of this as the photon is traveling, then it gets absorbed by an atom, it sits in there for a while, then it travels a little bit further, gets absorbed by an atom again, sits there again for a while, etc. And so the speed of light is greatly reduced. And then there were famous experiments done by a number of groups. Here's a setup from the Ron Walsworth group where they used not even laser-cooled atoms, but room temperature atoms in a cell. And what you can do also is you can influence via the intensity of the control field the speed of light in the system. And so basically, if you adiabatically turn this control field to 0, you can reduce the speed of light adiabatically all the way to 0. And this is what they did in these experiments. So they showed the so-called storage of light, where a light pulse was coming in, then the control light was extinguished. The light pulse was stored in the medium for a while, in this case, hundreds of microseconds, before it was retrieved again by turning on the control light. So this is, these are well-known electromagnetic induced transparency experiments and storage of light experiments. A number of people have done beautiful work on this, including Saikat, Ghosh. But these systems are typically or are all highly linear, meaning that you can store 1 photon, 2 photons, 3 photons, thousands of photons, and these temporal curves or spectral curves will all look the same. So how can we make it nonlinear? And this is, I should, by the way, say all that I'm presenting was done in close collaboration with Misha Lukin's group at Harvard. And with experiments performed both at MIT and at Harvard. These experiments were performed at MIT. So what we do now is we take this EIT system with a stable ground state, coupling to a P state. So for the experts, this is rubidium, this is the S state of rubidium, this is the P3 half state of rubidium, an unstable state that quickly decays. And so you can absorb and re-emit light. And then you have this classical control beam in this region. And then the idea is that this control beam couples the atoms to a high-lying Rydberg state. Think principal quantum number n equals 100. And so for our purposes, on the time scales of the light, this state is stable. The state typically lives maybe something like 100 microseconds or so. So it's, for all purposes here, it's a stable state. So we have a stable system where, instead of having this lambda system, we have now an excited state that is stable that we can couple into. However, and as I will show you in a moment, this Rydberg state is very special compared to ground states and has new properties that map onto those of the photon. So here again, we have the slow light polaritons. Now we're going up to the Rydberg state. And in our experiments, for instance, we typically have a speeds of strongly reduced speeds of light at the 1 kilometer per second level. So what are Rydberg atoms? You have seen already beautiful presentations and talks, I believe, by Tilman Pfau on this. So these are, think of hydrogen-like atoms, very high principal quantum number, say n equals 100 typically for our measurement. There's been much work done by interesting work by a number of groups here, some of which are listed, Matthias Weidenmüller, Adams, Tilman-Fau, and others. So the electron is very, very far from the nucleus. These atoms have very large dipole moments. They strongly interact with electric fields. For instance, Serge Roche used them for his groundbreaking work on cavity quantum electrodynamics with microwave transitions. But for us, what is interesting is that because they have very large polarizability, quantum fluctuations in one Rydberg atom can induce very strong responses in the other Rydberg atom and very strong Rydberg-Rydberg interactions. And so what that means is that here's an example, for instance, for n equals 100, the electron is as far as 1 micrometer away from the nucleus. So kind of 10,000 times further than in a normal atom. This is what the wave functions look like. For instance, for n equals 35, there's a large probability to find the electron far away from the nucleus. And these atoms have very strong van der Waals interactions. Basically, quantum fluctuations create an electric dipole moment in one atom, which creates an electric field. And then the second atom responds to second order perturbation theory, if you want, very strongly to this electric field, gets polarized. And so you get this kind of van der Waals interaction that goes as C6 over R to the 6. Now, what is important for us is that over macroscopic, or not macroscopic, but mesoscopic distances, or rather optically resolvable distances, this interaction can be large. So you can have tens to hundreds of megahertz of interaction energy in frequency units over distances of something like 10 microns that are easily optically resolvable. And that is key for all the work that I will be showing you, both on interacting photons, but also on interacting atoms. And there has been a large literature on this work. This is some of the early work. People, for instance, both in Wisconsin, Mark Suffman's group, and in Paris showed quantum gates between two Rydberg atoms early on. Electromagnetically induced transparency of Rydberg atoms was pioneered by Charles Adams's group in this work, for instance, already now 10 years ago. And this all goes back to theoretical ideas, in particular by Misha Lukin, Peter Zoller, and colleagues, how to use these dipole interactions to create strong nonlinearities, initially in the atoms, but also in the so maybe this is a good moment to stop for for a little bit and see just whether you have questions about electromagnetically induced transparency or this concept.
Yeah, I don't see any questions in the chat, Vladan.
Okay.
But I had a question, maybe, okay, Sadiq is asking, he has one. Sadiq, do you want to unmute and ask?
Yeah, I'll do that. Yeah, hi. So the question is actually, when you're talking about doing Rydberg atoms with and using Rydberg atoms as nonlinear media, because of the lifetime of the Rydberg atom, the energy density that you really require for the, I mean, you still require to put 2 photons or more photons within the lifetime of the Rydberg atoms. And when you have a whole pool of Rydberg atoms or a possible superposition of Rydberg atoms, how is that? I mean, how does the nonlinear coupling work out?
I hope to show you a little bit more in a moment. But you're right, of course, we need to put, to get interactions, we have to have 2 photons. It turns out that because of these strong interactions, as I will show you in a moment, when you put one Rydberg atom into the medium, it prevents the excitation with resonant light of any second Rydberg atom because of the strong interaction over a rather large volume. And so the density, the energy density you're talking about can be very, very small. In fact. So, photon rates of kind of 1 photon per microsecond or so are typically already, more than enough to elicit this nonlinear response. Not sure if that is satisfactory. Let me show you a little bit how to do that, and then maybe we can talk about this again.
Yeah, we can.
Makes sense. Any other comments or questions?
Well, I had a question similar, but for neutral atoms, that like this Magnon picture, if one just perturbatively kind of increases the probe field, what happens like when more than one atom starts making transitions? Is there a way of thinking about the dark state polaritons when more atoms starts?
Yes, there is. So basically, you can say that, you know, once one photon has been absorbed by the medium, you have now n-1 atoms remaining here. So the response of the system of these n-1 atoms compared to the original response, which was n atom, you know, the fractal change is 1 over n, right? You have a slightly different. In other words, when the photon number becomes equal to the atom number, then the response becomes strongly nonlinear. Right, okay. But the response in the nonlinearity to one photon level basically scales with the number of atoms. So you can have.
In terms of the magnon picture, I guess it gets into some sort of like it's not just coherent superposition of magnons anymore, right? Like it gets.
Correct. Yes. So you really have to think for the experts about the decay state in the system, and the decay states get then these different shifts due to the different couplings.
Okay. Okay. There is another question, Vladan. You want to take. So Mahesh is asking here, the intermediate P state is populated or is it detuned?
So we will, very good question. We will look at both. So first we will look at the intermediate state being on resonance. It turns out it's never populated. I forgot to mention it. Thank you for pointing that out. So in this free level system, you can be in a state which has destructive interference between the probe light exciting here and the control light exciting here. I forgot to say that. So basically, even though you're on resonance with the intermediate P state here, that P state due to destructive interference never gets populated. Because if it did get populated, it would decay very strongly and emit the photon into some other direction, and then you would have photon scattering. So thank you for pointing that out. So for electromagnetic induced transparency, it is crucial that you are in this so-called dark state and remain in so-called dark state. And dark means simply here that, you know, you have 3 quantum states. When you rediagonalize the system, you have 3 new states, and one of the states has such properties that the excitation, the P state, is very, very small, and therefore there's no photon scattering. Very good question. Thank you for reminding me of that.
Okay, I think you can go ahead now.
Okay. Okay, so now what changes when we do this with Rydbergs? So here we are coupling to the Rydberg state. You know, how do things work? So the idea is as follows. Imagine that we consider 2 photons that are far away in a medium. So there's some characteristic distance that I will define in a moment, which we'll call the blockade radius. Let's just consider one individual photon or 2 photons in the medium that are far away, further than some characteristic distance. Then for each of these photons, you have electromagnetically induced transparency. The blue is the control light. The weak is the weak probe photon. And because of this destructive interference that I just mentioned, there's no population in the P state, though we are right on resonance with the P state. So we are right on resonance S to P and P to R, but there's no population because of destructive interference. So the quantum state of the system is either the atoms here and 1 photon traveling, or 1 atom in the Rydberg state and no photons traveling, no population in the P state. And when these photons are far apart, they travel happily through the medium under electromagnetically induced transparency conditions at reduced group velocity as set by the strength of this blue control light. Now, what happens, however, if these photons come closer than the blockade radius? The blockade radius is defined as the distance over which the level shift, this van der Waals shift of the Rydberg atom, is larger than some characteristic line width of the system. So if the photons are less than, say, 15 or 10 micrometer, it turns out that the shift of the Rydberg levels due to the van der Waals interaction, so this is the van der Waals induced shift, exceeds some characteristic line width of the system. So now you can think of this Rydberg level as being far detuned from this control laser. So now the control laser, because it's coupling to a far detuned level, basically has no function. It is as if the control laser was not there. So we can remove the control laser from the system. So what you now have is just a 2-level system where, you know, the probe light couples the S to the P state, populates this P state. There's no longer destructive interference from electromagnetic induced transparency, and this photon very quickly decays. So very quickly, one of the photons will be scattered out of the system. This photon will be gone. And as soon as this photon is gone, For the single photon, EIT is restored because the Rydberg level, if you want, returns back to where it originally was. There's just now one photon in the system. You have electromagnetically induced transparency, and the photon alone travels happily through the medium. So what you expect is that you expect strong losses when two photons are close together, closer than a characteristic distance, and no losses or normal electromagnetically induced transparency when the photons are far from one another. So that's the expectation. This is the experiment, how we tested it. So we made an effectively one-dimensional system. We trapped laser-cooled atoms in a superposition of two laser beams, what we call a cross-dipole trap. And we arranged the situation in such a way that the sample was very elongated. It was maybe 50 or 100 micrometers along the direction of the travel. So this is the direction along which the light beams are traveling. And it was very small due to the laser cooling and the strong confinement across. So maybe a couple of micrometers across here. Whereas the beams and also the characteristic scale, this blockade radius is much larger than that. So it's an effectively one-dimensional system. We then shine in strong blue light, strong control light, that we filter out with an interference filter, and we send in then weak probe light along the same axis. And then to look at whether the photons are really interacting, we are going to look at coincidences on photon counters here. So we are going to look at so-called correlation functions of the photons. And as you know, if we have just laser beams, then the correlation function, laser beams, photons and laser beams obey Poissonian statistics. So in a laser beam, the correlation function, which is the normalized probability of finding two photons at some time separation tau, is just 1. So laser light has some very simple correlation function. And if we have nonlinear interactions going on between the photons, then we expect deviations on this correlation function from what we get from non-interaction. So that's the basic experiment. Here, as I said, to make the system effectively one-dimensional, we chose a beam waist, which was only 4 microns, which was less than about 10 to 50 microns blockade radius. Blockade radius, this simply means that two photons cannot travel side by side because of this Rydberg blockade effect. They can only travel one behind each other. So we have a very simple one-dimensional system. And as I said before, because of this Rydberg blockade effect, slow light polaritons cannot coexist within the blockade radius, so they can travel if they are separated by further than the blockade radius along the direction of travel, but not if they are overlapping within the blockade radius. And so basically the idea is also that the size of the slow light polariton, this is something I forgot to say, is small. So when you have a photon wave packet coming into the medium, and initially it travels at the speed of light, and maybe a typical wave packet for us would be 100 meters long. But then as the photon enters the medium, maybe I should go back to here. So here we have a wave packet coming in. And this wave packet is, maybe 100 meters long. But as the photon enters this medium, in this medium, the speed of light is reduced by a factor of 100,000. So now you have this coming in, and then suddenly the front edge of the pulse travels 100,000 times slower. So that allows the back edge of the pulse to catch up with the front edge, and it allows the photons to be very, very short. So basically the photons get shorted by, I will answer the question in a moment. The photon pulse gets shorted, but just by this ratio of the group velocities. So if the pulse was before 100 meters, it gets shorted by a factor of 100,000 inside the medium. So this pulse can now be inside the medium due to the slow group velocity as short as maybe a micrometer or 2. So here's a question from Sourav. In the description of the Rydberg blockade, is there really emission of photon from P to S state that can be detected? And the answer is, under these conditions, where the EIT is gone, indeed, yes. So this photon is scattered, when the photons are closer together in a certain distance, then this photon is really scattered out sideways. There is a real emission, and this photon could be in principle detected. Yes. So when you have EIT photons, on the other hand, then this P state is not populated and there's very little emission sideways. But when the photons are on top of each other, like in this situation, indeed, there is, in the blockade regime, the photons are just scattered on the S to P transition. Okay. So basically, let's see. Okay, so now we have, because of this slow light polarity and this enormous decrease in the speed of light, this photon wave packet is typically a few micrometers inside the medium. So it's really also smaller than the blockade radius, right? So this is the size of the slow light polarity term. Okay, so basically one way to think about it is, you have first this very long pulse and very weak pulse, maybe containing 2 photons, and they would be initially separated by a very large distance of, tens or hundreds of meters. And the blockade radius would be only 50 micrometer, but as they enter the medium, this pulse gets strongly compressed because of the slow group velocity. And now the photons find themselves, or the polaritons find themselves sitting on top of each other within this blockade radius of 10 micrometers or so, and start to be strongly interacting. So the first signature of that was when we plotted the transmission as a function of frequency. So this is the electromagnetic induced transparency. And so first, what you see here is that basically kind of the envelope of this is just that there's transmission away from resonance, and then there's no transmission on resonance. And then this narrow peak here in the middle region that I'm showing here, that is the electromagnetic induced transparency transmission. So here, there would be no transmission through the medium. The optical depth was rather 40. So the resonant transmission would have been exponential to the -40, a very, very small number. But then when the control light is there, we find high transmission. However, and this is crucial here, we find that this transmission is strongly nonlinear. So if you make the photon rate 1 photon per microsecond, we have about 60% transmission. But if you make the photon rate 6 photons per microsecond, in human units, an extremely small, extremely small light power, the transmission drops very strongly from 60% to something maybe like 10 to 15%. So this fact that the transmission is highly nonlinear already is a strong indication that there's a large nonlinearity in the system. But we can ask ourselves, is this nonlinearity classical or is it quantum? And for that, we need to look at quantum correlations. And so here is what happens when we look at correlations. So what we're plotting here on the vertical axis is the so-called G2 function. The G2 function is simply the probability of finding 2 photons. Let's pick 1 microsecond. So this value of the G2 function is simply the probability of finding 2 photons detected 1 microsecond apart, divided by the average probability, or by the average probability of seeing 2 photons that are completely independent, being 1 microsecond apart. So for a Poissonian distribution, as photons are in a laser beam, this G2 function would be simply 1, like we see down here. And so when we go to the Rydberg level n equals 46, which is not very strongly interacting, then you can see that the G2 function is roughly 1 for all times, maybe with a tiny effect near 0. However, when we go to this level n equals 100, we saw the G2 function drop very strongly, basically to the limit where at 0 time, meaning photons on top of each other, we almost never observe 2 photons on top of each other. So the probability of seeing 2 photons on top of each other was reduced to 13%, and when we correct it to background counts and detector errors, etc., it was as low as 44%, so 25% times reduction in the probability of finding 2 photons together. And this is exactly the effect that I've tried to describe here. When the photons are sitting on top of each other, or closer than some characteristic size, then one of the photons is scattered out of the medium, is removed from the system, and only one of the photons survives. And so the G2 function here really shows strongly non-classical optics. You can show theoretically that when the G2 function at 0 time is less than the G2 function at large times and less than 1, then you must have a quantum system. Classically, you cannot have light that has these kind of properties. Indicated here in a shaded region is the blockade radius. So if we take what we can calculate as the blockade radius, about 50 micrometers, and then convert it via the group velocity of the photons, which we can also measure, Vg, into a time, then this is the region where we should have excluded the photons. And what you can see here, however, is that this kind of nonlinearity region is a little bit larger than that. And now we understand that what is happening as the photon travels through the medium, actually the wave packet gets broadened a little bit due to dispersion. And so even photons that were not sitting on top of each other originally, because of the broadening, start to interact a little bit more strongly through each other, with each other. The system travels through the medium. in any case, this was the first strong indication or first strong proof that you can have a system where you send in a laser beam, a Poissonian distribution of photons, and then you have this filter, and out on the other side come individual photons, right? You never see two photons come out on top of each other. So you can think of this as a single photon source in some sense. Just by filtering out the two-photon component, you're left with wave packets of individual photons. So you have really a train of single photon pulses in transmission in the system. I think this is maybe a good time to pause and see if there are questions about this.
No, there is no question, Vladan.
Okay, so hopefully this was clear how this absorption works.
So I just wanted to ask one regarding this blockade. So this is just dispersion, which actually broadens the effective blockade size radius.
Yes, so it's basically just the fact that because they're going back all the way to this system here. Sure, whether can I? So basically, our wave packet, right, in frequency space occupies a finite width on this window, and so there's a dispersion in the system, which simply, as you said, Saikat, broadens the wave packet a little bit. So even if the photons were originally very small wave packets before traveling through the medium and far enough apart not to interact, then as they broaden, they have some finite chance of interacting.
Isn't the blockade radius actually set by the excitation, like the quantum number n value that it's like? Isn't it that?
Yes. So the blockade radius is set by the quantum number n and is fixed, but the size of the wave packet can change due to the.
Okay.
So kind
because
of in this
effectively a polar return.
Yes. Right. So basically, in this picture, in this very simple picture, right. Well, the size of this wave packet can broaden as it travels through the medium and therefore can have some interaction.
Okay, you can go ahead.
Okay, there's another question. When the pulse gets compressed inside the medium, does it also broaden the photon frequency? No, it does not broaden the photon frequency. So basically, what is happening is frequency, just like energies are conserved. So the frequency spectrum of the photon remains the same. Very good question. But what happens here is that basically, going back to this picture here, so because of the strong dispersion, the group velocity is reduced. But you can think of the photon wave packet as occupying some certain frequency space here, and that frequency spectrum of the photons is actually conserved in the system, apart from effects that come from the interaction.
Yeah, there's one more question from Niranjan, that is it right to say that we see blockade-like effects even though the Rydberg state is never occupied?
Not quite. So the Rydberg state is actually occupied. In this system, let me go back to this one here. So the Rydberg state is actually occupied. What is not occupied is the P state, the broad state of the atoms, where we have absorption. So the Rydberg state is actually occupied. So and it's occupied most of the time. So if you look at this polariton picture, the fact that our group velocity is reduced by 100,000 compared to the speed of light means it's 100,000 times more likely to find the Rydberg atom in the medium, if you were to measure, than to find the photon traveling through the medium. So the Rydberg state is occupied most of the time, I would say. But the P state here, this intermediate state, which is not the Rydberg state, is not. So this is, I should have labeled this maybe. This is the 5s state, ground state of rubidium. This is the 5p state of rubidium, the first excited state, no Rydberg. And then this is the n equals 100 state. Thank you for the questions.
Okay, yeah.
Let's see, anything else?
Yeah, I think.
All right. Yes.
Yeah, there's one more question from Mahesh. How to make sure in experiments that atoms are in Rydberg state? What is the detection scheme?
So we are actually never detecting the atoms in the Rydberg state. All that we are ever detecting is the photons in this experiment. So we just use the fact that they are excited to the Rydberg state. And we can measure, for instance, we can spectroscopically find the Rydberg state by tuning the lasers and looking at absorption, dispersion properties, etc., where the Rydberg states are, but we are never actually measuring the Rydberg atoms. So in this particular experiment, we are just measuring the photons coming out of the system. In experiments that I will be talking about tomorrow, we measure Rydberg states indirectly. Basically, we remove the Rydberg atoms through a process from the sample, and then we would measure that as a loss. But in this particular experiment, we never measure the Rydberg atoms directly. We just use their properties while the photons are traveling, and we infer everything from photon measurements on the system. Very good question.
Okay, I think you can go ahead now.
Okay, very good. Thank you for so many questions. It's much more fun and I think more useful if we discuss it because it's a very unusual nonlinear system. Okay, so here I have shown you dissipative, strongly dissipative quantum effects. Basically, we have, if you want a two-photon filter, as I said, it's a system where one photon travels happily through the medium without ideally any absorption, and two photons through the medium. One of the photons is removed, and then the remaining photon travels through the medium. So the absorption is very, very different for two photons than for one photon. It's like an absorptive filter, but strongly nonlinear. Two photons are removed, three photons are removed, only one photon can travel through the medium. It's like a very strongly saturable filter for people working in this area. Saturable filter, attenuation filter is something that saturates and lets through more photons. This is like the opposite of the saturable filter, where it lets through one photon, but two or more are simply removed. But one can ask the question, instead of looking at dissipation, can we look at force? Can we look at dispersive effect? Can we look at something that is to lowest order energy conserving, but has strong nonlinearities? And it turns out that this can be done, and it requires just a tiny little change in the system. So now what I have done is I have detuned the probe light from resonance, from the S2P resonance, by a few line widths. So the P state has a certain line width for 6 megahertz. We detune this light maybe by 20, 30 megahertz from resonance. The probe light is now detuned from the S2P resonance. This goes back to some questions that somebody asked me at the beginning. And at the same time, we detune the control light by the same and opposite amount, so that we are still on two-photon resonance. But what I mean by that is when we absorb a probe photon and then absorb a control photon, we are still transporting an atom from the S to the Rydberg state. But we are now detuned from this intermediate P state. Nonetheless, if you go through the calculation, you can find that destructive interference still works, and you still have in this system a cancellation of the effects of the P state. In this case, you cancel not only the absorptive effects of the P state, but also the dispersive effect of the P state. So basically, in this system, you have an index of refraction of 1. It is as if the P state wasn't there at all, except for this. And you have otherwise an index of refraction of 1. Of course, you have electromagnetically induced transparency. But we are off resonance. So again, now when we have two photons that are separated by more than this blockade radius of maybe 15 or 20 micrometers, then these photons travel happily through the medium that essentially no absorption. And there's almost no dispersion. However, when these two photons are again closer to the blockade radius, now the Rydberg levels due to the interaction are shifted away from resonance. Again, same argument as before, we can forget about the control laser coupling the system, and we can forget about the Rydberg state too. They were not there. Now what we have a two-level system, but unlike before where the S2P light, the probe photon light on resonance and get strong absorption, now because we are detuned by a few line widths, we have strong dispersion rather than strong absorption. So the dominant effect now when we're off resonance by some detuning delta, which is larger than gamma, the dominant effect is the index of refraction posed by the atoms in the S state. So basically an index of refraction and photons are close together. So what that looks like, for instance, here is if we plot the phase of the transmitted light, we can measure a heterodyne technique as a function of detuning. Excuse me. Then we see two resonances. One is the normal two-level resonance. Detuning 0 means S2P transition. So this is the normal resonance that we're not very interested in. And then the other one is this EIT resonance, two-photon resonance, where basically we have another line here that is associated with the two-photon transition from the S state to the Rydberg state while being off resonant from the S2P transition over here. And at this point here, this is the EIT point for the tuned system where we have no phase shift, no dispersion of the system, and also our transmission is high in the system. And this is what the curve looks like. And now again, the blue light was taken for very small rate of photons, the blue curve, and the green curve was taken for a 10 times larger photons. Again, these rates are in absolute units, very, very small, a few photons per microsecond, but you can clearly see a different phase between the blue curve and the green curve, right? Which indicates again a strong nonlinearity. So I should point out, so the slope here gives us the group velocity, which in this case again is about 1 kilometer per second. And then it turns out that this system also has a curvature. So the phase or the energy as a function of frequency or as a function of d omega over dk, there's also the second order term d squared omega over dk squared. So the quadratic dispersion also leads to a finite mass of the photon. So whenever you have linear dispersion, you change the group velocity. When you have a quadratic dispersion, remember simple waves, whenever you have quadratic dispersion, you have an effective mass, and depending on the sign of the dispersion, this mass can be positive or negative. So what we have is not only slow photons, but because of this residual curvature, we have also massive photons. To calculate the system, you can think of this photon mass as roughly speaking something like 1 electron mass for the parameter that we are using, and you can tune it by tuning the strength of the control light. Okay, so what does the system look like? Imagine that we have this medium and the first photon is somewhere here at this location. Then if the second photon is further away, it experiences this blue curve. If the second photon is far away, it experiences this index of refraction n1, which is approximately equal to 1. So basically, if the second photon is far away, it experiences this blue curve where the phase shift is 0, or equivalently the index of refraction is 1. However, if the second photon finds itself closer than the blockade radius of the distance from the first photon, the second photon is within this distance, then it experiences a different phase, a different index of refraction, because it's like the green curve over here. So basically what we have is like a little glass plate, right? Index of refraction of think 1, then n2 larger than 1, 1, and 1. So it's like a glass plate, but the glass plate is now traveling with the first photon. So wherever the first photon is where this region of increased index of refraction is. This is the index of refraction experienced by the second photon. So we know, of course, what happens in such a medium. We have intuition. Basically, the wavelength is changed. So if you had a certain wavelength out here, the photon frequency, going back to another question was there before, the photon frequency is not changed, but because the index of refraction is changed, the wavelength is changed inside the medium. But because we have a massive particle here, it turns out that to lowest order, we can describe this quite well by just the Schrödinger equation. Even though these are photons, these photons are slow, they're non-relativistic, and they have mass. So it turns out that the approximate equation that you can write down is very similar, or is the same to lowest order as a nonlinear, as a Schrödinger equation in one dimension with an index of refraction. And if this effective change in index of refraction is such that the wavelength is shorter in this region, basically that we have more energy in this region, then you know from the Schrödinger equation in one dimension that any attractive potential, and this attractive potential enables a bound state. And if this potential is weak, meaning if its range is small and or the depth is small, then this bound state is mostly situated outside the region of the potential. Like this is kind of like the delta function limit. So we expect in this system a bound state, and we expect in this system now a bunching of photons, a higher probability of two photons arriving on top of each other. And we also expect a phase shift. So how do we measure this? We measure at the same time as before, this cloud that I've shown you, one-dimensional system, etc. What we had added in this experiment is we added more than 2 detectors. We added up to 4 detectors. So basically that we could look, as I will show you in a moment, also at the higher order correlation functions, not only for 2 photons, but also for 3 and 4 photons. And we also set the system up in such a way that we can also measure the phase, not only the photon arrival time. So to measure the phase, what we do is we work with photons of a certain polarization, sigma plus light. We can send in a sigma minus reference beam, which is on a weak transition and far away from resonance, that serves as our reference beam, so that we can essentially do a homodyne detection of the phase of the probe photons that interests us relative to this unperturbed sigma minus light traveling through the system. So depending on how we set up our detectors, we can either measure photon arrival times, G2 functions, or we can measure conditional phases. And quantum tomographically, we can reconstruct the whole wave function. So what do we see? First is the probability of finding 2 photons. And now you see that we have a peak at 0. So now the photons before, we had small probability of finding photons on top of each other. Now we have a large probability of finding 2 photons, an increased probability of finding 2 photons on top of each other. And if we plot it not as a function of time, but as a function of distance, then the green curve indicates the blockade radius. And we can see that as we expect for a weakly bound state, most of the probability to find 2 photons is actually outside this bound state region, simply because our bound state is weak. So this is almost like a delta function or a very short range potential, where most of the bound state amplitude is outside this region. So we have this 2-photon bound states. We can verify things in various ways. We can, for instance, plot, the G2 function, arrival time of photon 1, arrival time of photon 2 on the other detector. And then what we see is a pronounced peak when the arrival times are the same. So the photons like to arrive on top of each other. And there's also a depletion region where the photons, basically, if they were originally arriving at a certain small time distance from each other, they now get attracted and sit on top of each other. And we also could measure the phase. The lower plot shows you the phase here. And again, we see a strong phase shift if the photons arrive within a certain time distance, small time distance on top of each other. And this phase is the larger, the smaller the tuning from resonance. So basically, when you go closer to resonance, the index of refraction is larger. So the phase shift increases, but at some point you can't get too close to resonance before dissipative effects dominate. So there's some optimum around a few gamma where you see a relatively large phase shift, but not too much dissipation. And so here the largest phase shift that we saw was about pi over 4. So not enough to make a 2-photon gate, quantum gate, for instance, but enough to be a sizable fraction of pi. We can also plot things in other ways. For instance, we can look at the so-called concurrence, which is a measure of entanglement between 2 photons, and we could show that this system, simply the transmission of light, laser light through the medium, leads to an entangled state of the photons without anything else to do. And maybe before I take further questions, one more disclaimer, right? I've talked about photons, but I should be really talking about polaritons, about these quasi-particles inside the medium. But of course, we don't detect them inside the medium, we detect them outside the medium, right? So how does that work? So one way to think about it is you have these independent photons coming in a laser beam. So the G2 function is 1 at all time separations. The probability, basically the Poissonian distribution says the probability of finding 2 photons at time interval 10 microseconds is the same as the probability of finding 2 photons at time interval 1 microsecond is the same as the probability of finding 2 photons on top of each other. So these are independent photons in a laser beam. Then we have, while the system is inside the medium, we have these bound quasi-particles of polaritons inside the medium. So the polaritons are the ones that are really bunching or sitting on top of each other. Here's where the forces are acting, if you want the effective forces on the system. But then, the photons leave the medium, the forces stop acting because they are now in vacuum, there are no more forces. But because vacuum has no dispersion at all, whatever was the wave function inside the medium gets maintained as the photons travel through vacuum. And that's why we can observe these photons. They now just stay exactly where they were inside the medium, even they are no longer interacting with one another. And that's why we can see them. Here I have a good question. It says, how do you measure the phase shift between 2 photons? So what we do is the following. Very good question. Let me go back to the setup. So we send light. The sigma plus photons are the photons that are interacting, that we want to measure the phase of. We send also some sigma minus light through the medium. And this sigma minus light, you can think of it as detuned from resonance, etc. The interaction is weak, so this sigma minus light is a phase reference. So what you have, say, on this detector here is a superposition, is a beat node, is a phase sensitive signal between the sigma plus light and the sigma minus light. Or in other words, if the phase of the sigma plus light shifts phase relative to, if I have a certain superposition of sigma plus and sigma minus light, say with 0 phase, it corresponds to linearly polarized light. If now the phase is changed of the probe light by some phase, then this linear superposition will be again a linear superposition of I should say linear polarization of light, but it's linear polarization of light as a rotated angle. So basically, by analyzing the polarization of the light coming out, this is a polarization beam, or this one here rather is a polarization beam. So by analyzing the polarization of the light coming out, we can measure the phase shift. A phase shift of 0 means no polarization change of the light. A larger phase shift means more polarization change of the light. Now we want to do this in a conditional way. So what we do is we look at the clicks on this detector, the polarization of the light on this detector, conditioned on having seen a photon at time t equals 0. So basically say this detector clicks, and then to generate this phase shift curve, say at 200 microseconds, we look at 200 microseconds later, what is the ratio of probabilities to find a photon on this detector, which tells us the polarization of the light. So hopefully that helps. So these are conditional phase shift measurements. Very good question. Okay, so we can also do this with 3-photon bound states, same experiment as before. In this experiment, we slightly changed the setup. So instead of using the sigma minus light transmitted through the medium as a reference, we now choose a local oscillator derived from the same laser, superpose that on some technical advantages. Because we can make this local oscillator stronger, we superimpose that on the light. So on this detector, we can now measure phase shift through a heterodyne technique, basically by looking at the beat node. This local oscillator is shifted in phase, so shifted in frequency. So any phase shift on this light transmitted through the medium shows up as a phase shift of the fringes of the detector D3. And then we can condition this phase, for instance, on detector D3 on having seen 1 or 2 photons on detectors D1 or D1 and D2, etc. So we can also measure 3-photon phase shifts. So if you have a 2-photon phase shift, I said we have a 2-photon weakly bound state. So if you have 1 photon here, then the second photon is bound. Imagine that we detect 2 photons, say within some small distance of one another. Then we have kind of 2 attracted delta function potential. So we expect now the third photon to be more strongly bound, simply because it has 2 attractive regions here. So think of this as a delta function. Everybody has done that in elementary quantum mechanics. Single delta function, you have a certain interaction strength, a certain binding energy, a certain size of the wave packet. If you have 2 delta functions, then the size of the wave packet is changed, and you have this extra interaction term, and you have in general just a stronger binding. So, if the delta functions are close to one another, then the binding energy you expect to quadruple. So what we expect in general is the 3-photon bound state is more strongly bound than the 2-photon bound state. However, we also have some effects. So basically, if the photons are sitting exactly on top of each other, then already one Rydberg excitation saturates the medium, and then the second photon has no effect. So there's also a saturation effect of these delta functions. So basically, if the photons are close together, the binding is stronger, but if the photons are on top of each other, the binding is again a little bit weaker. So what do we observe? Here now I'm plotting in a 2-dimensional plot the probability of seeing, basically this is the arrival time difference between 2 photons, photon detectors 1 and 2. This is the arrival time difference between detectors 2 and 3. So the lines correspond to 2-photon bound states. So for instance, this line corresponds to, T1, 2 detectors click at the same time. We have a higher probability of 2 photons coming out of the system. And then the third photon arrives at some other time and has nothing to do with the system. So these would be the 3 lines correspond to the possible 2-photon bound states. But what we then see in the middle is a very strong blob where basically all 3 photons come out at the same time. So basically in this system, we have a strong bunching of 3 photons. And here, if we plot that against the single axis like so, then the red curve here, or the brown curve, is the 2-photon G2 function. And then we can see that the G3 photon wave function, G3 correlation function, is both higher and also more importantly, is more strongly bound, more strongly decaying, works over a smaller distance. So we have 3-photon bound states. And we can also look a little bit like in this delta function picture. We can, for instance, look at what the bound state looks like as a function of the distance between the 2 photons. So if we post-select on having observed 2 photons within 100 nanoseconds or 200 nanoseconds or 500 nanoseconds, we can then plot the arrival time of the third photon post-selected on this condition. And so, for instance, what we see here is, if basically the 2 photons arrives 2 microseconds apart, at -1 and at 1. Then the third photon either binds to the first photon or to the latter photon. We have just a 2-photon bound state. So the third photon binds here or here. But if we post-select on the photons being closer and closer together, like only maybe 100 nanoseconds or even on top of each other, then you have something like a binding of the third photon to both. There was a question as why is there oscillations in the free photon G2 function? Let me just look at that. Here, some of that is real. It's basically a wave dispersion effect when you go through the system. So our system has a finite size. And so basically probability, if you want, gets pulled in towards the middle. But then, there's, it's not perfectly smooth because in the finite size system, oscillations maintained. So maybe I'll show you. We had something like here, something similar to happening here, even in the 2-photon system, where you see both in the calculations and even in our data, there are kind of regions where the wave function oscillates. We think that these are finite size effects of the system. The photons travel a finite time. Good question. Okay, maybe let me stop briefly here before I come to the very last part on making repulsive interactions between photons. Are there questions about this? Okay,
yeah, so there's a question from Mahesh, like 2-photon detected at the same time and third photon at other time. Can I say this? In this case, 2 photons were at Rydberg and one phase the blockade.
Yes, you can with a caveat. So, so if the 2 photons came at a small time, if the 2 photons came at a small time separation, less than the Rydberg blockade, then indeed you would have one Rydberg atom at this position, right? Time and position are equivalent. And so basically 2 different times correspond to different positions. So if we are in this situation down here, then one Rydberg atom is in one position, the second Rydberg atom is in a slightly different position, and then the third photon experiences those 2 Rydberg atoms and then binds in some way to them, experience the index of refraction. However, if the 2 Rydberg atoms or the 2 photons were exactly on top of one another, then already the first atom gets excited to the Rydberg state, and now there's this Rydberg blockade effect, so no second Rydberg atom can be excited. So in this regime, where they're really sitting exactly on top of each other, actually only one Rydberg atom is excited, and the other 2 photons are bound to it. So there's a transition. It's really similar to the delta function. So in this region here, where the photons are really on top of each other within a small window, we should have only one Rydberg excitation and 2 photons, 2 other photons traveling or bound to this system. Whereas here we have 2 Rydberg excitations, for instance. Very good question. Does this answer your question, Mahesh?
Yeah, I think that's saying is that's clear. Yeah.
So this is the thing that I meant. There's a saturation of this force. Can one think of the single photon source using micro-sized vapor cell due to EIT in the blockade regime? I think that's one can think about that, and it's a very attractive prospect to make single photon sources, that are more practical. Our system is a big experimental later cooled atom, not really a good source. If this system can be made coherent enough in a micron-sized vapor cell, then one could think of using this indeed as a single photon source, and it's a promising perspective. Another perspective one can think about is whether somehow, this principle is very general. All that we have is we have strong interactions at small distances. One can even ask oneself, is it possible to find a crystal where one has similar conditions as the Rydberg blockade, where basically 2 excitations in this crystal or in this glass maybe interact strongly with one another. So one could even go further and say, is it possible in a solid state medium to have the same physics? And if that were possible, then you would have really a device you could sell, right? If you could have a solid state device, maybe also the micron size vapor cell, but even even better would be, in my view, a solid system. If you could sell a little device where you send in a laser beam on one side and simply single photons come out on the other because of this blockade physics. It's a very interesting question. One of the challenges is that in a thermal cell, and small size, you have, of course, the wall interactions. And so you have to make the interaction strong enough. So put it another way, maybe this is a good time to explain this, because this is a very good question. So when I define the blockade radius, right, what defines the blockade radius? This size here, it really is defined by the distance where the van der Waals shift C6 over R to the 6 is larger than the line width of the system. And line width of the system is the line of the two-photon resonance from S to R, right? So here, for instance, you can see the line width in our system is typically less than a megahertz, maybe a few hundred kilohertz to a megahertz. So if the line width is larger, then basically I need stronger interactions to shift out of resonance, and then the blockade radius shrinks. So if in the, say, microcell, the line width of the EIT resonance is 10 times larger, then there's a, 6 root of 10, there's a smaller blockade radius associated with that. So one has to keep that in mind, but it scales relatively favorably. So I would think, it's a promising direction to explore. Thank you for that question. Okay, we are almost at the end. Finally, I would like to tell you about a challenge that we had for a number of years. Let's see. Is there another question or just a thank you? Okay, no question. Can we make repulsive interactions between photons? And then you would say, well, of course it's trivial. You would think that, of course, it's trivial to make repulsive interactions. If I go back to this picture here, you can just change the tuning, right? So here I chose a positive detuning and I have a certain slope of the system. If I chose a negative detuning, if I tuned this probe laser below resonance, right, then everything would invert, and then I would have the opposite slope on the other side. So it should be possible to simply, by changing the detuning of the laser, to change the potential, interaction potential from one sign to the other sign. So you can flip the potential from attractive to repulsive simply by going to the other side of the resonance. The problem with that is when you invert the system is that the curvature term, this effective mass term, also changes. You can kind of imagine if I do a mirror image of this, then the curvature term will be opposite. So when we change the tuning from the one photon in resonance, from the S to P resonance, what happens is that the mass term gets the opposite sign. So yes, we are switching the interaction term from attractive to repulsive, but we're also switching the mass term from positive to negative. And a negative mass in a repulsive potential is very much like a positive mass in an attractive potential. So it turns out on the other side of the resonance, we cannot really control this because we cannot control the sign of the mass and the sign of the interaction independently. So that bothered us for a while. And then finally, we figured out in this paper how to do repulsive interaction. And one solution was to add another level. So basically, this is our Rydberg EIT level where we have interactions. We did also another level where we added normal EIT. So we have not only now one control laser but a second control laser, omega F called here, which couples to another ground state. This state is not strongly interacting. All the interactions come from the Rydberg state, but this state has a new detuning. And what this simply means is that because we have now two parameters, we have two control frequencies, you have kind of one extra parameter where you can in principle tune independently the sign of the mass term and the sign of the interaction term. So it turned out that in this more complicated system, which is more like a star EIT, if you want, with two stable states, the state F and the state R, in addition to the ground state G, there one has one more knob to turn so that one can independently tune mass and interaction. So for instance, now what is shown here in the detuned regime is the transmission curve for EIT with both of the coupling lasers on. So this broader feature here is coming from this blue omega R laser. And then inside this broader feature, we imprinted another narrow feature, which comes from this orange laser. Very good question. Let me answer this question first. Is it possible to obtain such photon-photon interaction using Coulomb blockade of ions and ion traps? And the answer is, in principle, yes. However, you need to have many ions, enough ions to make the system optically dense so that your photon has a high probability of being absorbed. And if you do that, if you can have many enough atoms in an ion trap, then it's definitely possible to use the Coulomb blockade of ions for the nonlinearities. A very good remark indeed. Okay, so here we go now to this more complicated structure where we have kind of a double EIT. And now you can see inside here we have another parameter of freedom where we can choose the transmission and the slope, etc., to make, to basically tune mass and potential separately. And when we did that, let me just remind you what we expect for attractive potential. We expect this bunching feature, right? Photons liking to become on top of each other. And then for the repulsive potential, we expect this anti-bunching of photons feature, which we saw in the dissipative regime as well, but here we should have it without photon loss. So basically, the photons should be repelled from this inner region, but then there should be higher probability to find the photons at finite distance in a finite medium because they have been pushed apart by a certain distance. And indeed, when we tune the parameters, this is what we see. On the left-hand side is where we tune things into repulsive regime. You see now the G2 function is less than 1 and 0, anti-bunching, and then the probability is pushed out towards some finite distance. So the photons repel each other, whereas here we have the attractive regime where the photons are, as before, binding with each other. There was a question why yellow laser EIT responds finer than blue. There's no particular reason. You can identify different regimes. You don't want these two EIT resonances to cancel each other. So as you can see, they have kind of opposite tunings here in some sense. You want, not necessarily, you could also be working in the opposite regime where the omega F coupling strength is larger than the omega R coupling strength. I think if they both are the same, I'm not sure whether you can still get repulsive interaction, but there are certainly several parameter regimes where you can get this effectively repulsive interactions. This was more or less just one regimes that we chose. Good question. And so you can see here by tuning the detuning of this extra laser, we could switch actually from attractive to kind of nice repulsive physics between the photons. The same here done in a 3-photon regime. Again, distance between 2 photons, 2 detectors, distance between 2 other detectors. The lines correspond to the 2-photon repulsion. And now we have reduced probability of finding photons at finite distance from one another. But then in the middle, we have also this stronger 3-photon repulsion where basically the photons go out. And as a final graph, similar to what we did before with the binding of 3 photons, we can now condition on seeing 2 photons at a certain distance, say a large distance or a small distance, and then plot the probability function, the probability for the 3rd photon. And so you see here the photon is repelled either by the 1st photon or by the 2nd photon, and if we bring these peaks closer and closer together, we start to see some interference between these 2 bindings. So basically the photon wave function being repelled from one side and from the other side is now increased in the middle, as you can see, for instance, at this distance. So at this distance now, the photon is kind of the middle photon here. This photon 1 is repelled from both sides, so it has a higher probability of being symmetrically located between the 2 peaks. And then finally, if they're sitting on top of one another, we have just a stronger blockade than before. For a single photon, we have now a stronger blockade for 2 photons. So that brings me to the end of my presentation. I can take some more questions. So I've shown you that one can use Rydberg interaction to generate highly non-classical optical devices where 2 photons really behave differently than 1 photon and 3 photons behave differently than 2 photons. For instance, this 2-photon absorptive filter or 2 or 3 photon bound states. As I said, I used photon language rather loosely. These are really polaritons, these quasi-particles inside the medium that, however, maintain their photon character as they come out of the medium. And then this is something we already discussed. Can one apply this? This was a good idea, maybe to miniature vapor cells of Rydberg interactions, or even, to solid-state systems, that one can build real devices that maybe a company could produce and sell to you, so that you can have a photon source for your future measurements. And then there may be applications of this for quantum communication, quantum networks. It says why 3-photon coincidence detection area is a little elongated along the y-axis. You mean why it's wider here? If you mean that, I think that's just
regarding the center region. The center region, it seems there's an asymmetry along the diagonal.
I
see.
see.
All three photon detection in all three plots you have. So that circular region, that is not circular, little elongated along that axis.
I think it's just a question of projection, in the sense that if you look at this distance along the horizontal direction for this line, it has a certain width. This line looks narrower, but it has the same width along this direction. So I think it's just the way we are plotting this, I believe. It's a good question. I'm not sure.
Earlier two plots, those square plots also, I mean.
Okay, it's a good question. Yeah. In principle, these detectors should be equivalent. So there shouldn't be a difference between the detectors. Let's just see. It's a good. Yeah, this one also looked a little bit elongated diagonally. I think that there's definitely effect from just the projection. This diagonal axis is somehow special, right? But I have to think about it. I'm not sure, but I know the answer to that question. I think there should be no physics associated with it, because I think the detectors are set up to be symmetric. In other words, the T1 detector is used twice, right? So the times are really the times of detection. So here we measure the detection distance between detection time between detector 2 and detector 1, and here we measure detection time between detector 3 and detector 1. So the detector 1 in some sense is used twice, not fully symmetrized. Okay. Are there other questions? We had a lot of questions during the talk. Thank you for that.
There's nothing in the chat box, so maybe I can ask while others type in or something. So these experiments are done with coherent states, right? Like just weak coherent. So, so the fact that they are actually not conditioned on single photons, do you see any effects of like the fact that these are actually, like, you might also have probabilities of detecting 2 and 3 photons?
Exactly, yeah. So that's a very good point. So when we detect 3 photons, we sometimes have, for instance, 4 photons in the system. When we detect 3 photons, assuming there are no detector dark counts, we know that we didn't have 2 photons in the system, but we could have had 4 photons in the system. And these contribute an impurity that we can, in principle, make smaller by making the coherent state weaker, right? But then our detection rate goes down. So that's a very good point, Saikat. If we had really a 3-photon source, our data should look better because they're contaminated by the photon effects. So all that we can do is make the photon rate sufficiently small that this effect be 20%, 50 or 100%. Very good remark. That's what limits us, for instance, from detecting 4 photon states, because they occur so rarely if we want to keep the probability of having 5 photons in the system small enough. But we believe they are partly responsible, for instance, why we don't see super regular patterns and crystallization in the system, because we have sometimes more photons than they would say 4 photons would definitely rearrange themselves differently than 3 photons.
So there is one question in the chat. Yeah, do this double EIT process cause heating in the system? Is it coherent throughout? Yes, so it's moderately coherent. I mean, we see these nice dispersion curves. I didn't plot plot here the transmission and so on. It's not perfect, and we see some additional dissipation that we don't understand. We really don't know where it's coming from. So when we turn off one of the beams and have either the yellow EIT or the blue EIT, we can infer a certain line width of the system. If we have both the blue and the yellow EIT on, our line width is reduced. And that's something we were not really able to fully figure out what's going on. Why it is that the width, the coherence of the 4-level system is worse than 3-level, and what we would calculate from the individual measured 3-level. But it's sufficiently coherent to see the effect. But there was definitely some broadening, and have a cleaner system that works better. It's very good. We're not sure. There is some additional effects in this 4-level system we don't fully understand. So if I just continuing on this question, if I think of these 2 different EIT processes as 2 dark states, So the dark state with the Rydberg state is actually very broad, right? Like very short-lived because there's an excited state. So there's a two competing kind of very different line with polaritons kind of forming. So
exactly, and then we are trying to address for these repulsive photons a certain detuning from the other dark polariton, so that we inherit certain properties of that polariton, so that we can tune, for instance, the curvature, meaning the mass and the interaction separately. But that's exactly the correct picture. We have two dark state polaritons of different lifetime, different widths, and then at a certain point in the spectrum, we can get these effectively repulsive interactions. But I would say this is not, I would say I don't understand it intuitively well enough. I mean, we can do calculations and, find how it works, but it would be nice to have a even better, double rest state understanding of what is really going on in the system. For instance, where we found these resonances, we would not have quite intuitively predicted that they are there. We just calculate them and measure them together.
So I had another question. So this is basically like with the 3-photon bound state. So the data, like you are basically detecting them and the states through post-selection, which is basically telling us that you had this 3-photon bound states. Are there any secondary ways of actually directly detecting so that they can be on-demand kind of 3-photon bounds?
Well, I think, first of all, you would like to send in 3 photons, right? I mean, it's always a filtering process because we have this incoming laser light, right, which is a coherent state, which is then projected either onto, basically filtered, right? It's either projected onto the 3-photon component as the system enters or discarded. You could imagine that you could have some kind of adiabatic evolution where the coherent state adiabatically evolves and completely maps onto the ground state. Maybe if you tune the density to be, slowly varying or something. We don't quite understand this, but we are also always limited by the finite size of the system. But you could imagine if you had a very long system that could be able to range itself the way that adiabatically forms from the coherent state. But we have always some kind of projection.
Yeah, and that is where, like, in that kind of an adiabaticity, because you have these two competing time scales for the two polaritons, so you need to be slower than the slowest. Right. And there you might actually decay out with the shorter-lived polariton, or I don't know whether that's the right way of.
It probably is the right way to think about it, and I think it would be really nice to understand that a little bit better and whether that poses, for instance, fundamental limits. I mean, for us, we would have liked to see a crystal. What prevents us from seeing a crystal is that crystal is always formed by short-range repulsion plus long-range attraction, right? Otherwise, the system just explodes. For us, we don't have the long-range interaction at the moment. So the reason why these photons look crystallized is because the interaction length of the medium is finite, right? You have these 3 peaks because they separate the surface. But, it would, for instance, also nice. You could imagine scenarios where you have a long-range attraction, a real crystal photons. And that might be even more valuable than a single photon. If you could make, 5 photons coming out the side at that time.
Okay, is there any other? I think there's no other question. If anyone has any questions, can just turn on. I think we are also just past the time.
Yes. All right. So just as a preview for tomorrow, I'll show you, arrays in 1 and 2D of individually trapped atoms, and basically quantum phase transitions in the system, where we have now pushed the qubit number to over 250 individually addressable and controllable qubits. So it's an exciting field, and I look forward to seeing you guys again tomorrow.
Okay, thanks a lot, brother. Thanks a lot.
Well, I'm sorry, tomorrow we will start half an hour later because I have my last class to teach, and I can really not miss this one. I'm teaching quantum mechanics.
Okay, great. So for everyone, just to remember, we'll also send a reminder mail that tomorrow we will start at 8:30 Indian time. Okay, thanks a lot, Vladan. So I guess we can stop here for
Sourav,
today.
I'll answer your question next time about 2 different Rydberg states. It also applies.
Okay, no problem. Yeah, sure.
Bye, everybody.
Yes, bye.
Bye.
Yes.
Bye.